Have you ever stood next to a running car engine and felt the vibration move through the ground beneath your feet? That sensation, that raw mechanical energy contained in something roughly the size of a suitcase, feels impressive. It feels powerful. But it is nothing. It is so far removed from the upper limits of what human engineering has actually achieved, the comparison barely makes sense. Today we are going to talk about the most powerful engine ever built. And I promise, by the end of this, the way you think about power, scale, and what machines are actually capable of will never be quite the same. To understand what makes an engine truly extraordinary, you first have to agree on what power actually means in this context. Power is not the same as force. It is not the same as speed. Power is the rate at which work is done. How much energy can be delivered, and how quickly. The unit most people are familiar with is the horsepower. A typical family car produces somewhere between 100 and 200 horsepower. A high-performance sports car might reach 600. A Formula One car produces around 1,000. These numbers feel large until you understand what sits at the other end of the scale. The most powerful engine ever built for commercial use is the Wärtsilä RT Flex 96C. It is a two-stroke diesel engine designed to power the largest container ships in the world. And the numbers attached to it exist in a different universe from anything most people have encountered. The RT Flex 96C produces 107,000 horsepower. To put that in context, that is roughly the equivalent of 107 family cars running simultaneously at full throttle. It is more power than the entire fleet of Formula One cars on a starting grid combined. It is more power than the engines of a fully loaded Boeing 777, not just one engine, the entire aircraft multiplied several times over. One machine, one engine, 107,000 horsepower. But the horsepower figure alone does not tell the whole story. What makes the RT Flex 96C genuinely extraordinary is not just the peak power it produces, it is the torque. Torque is the rotational force the engine delivers to its output shaft. In a car engine, torque is measured in Newton meters and typically peaks at a few hundred. The Wärtsilä RT Flex 96C produces torque figures so large they are almost impossible to visualize. At its operating speed of around 100 revolutions per minute, it delivers approximately 5.6 million Newton meters of torque. That is not a misprint. 5.6 million. Now here's what is remarkable about that operating speed. 100 revolutions per minute is extraordinarily slow for an engine. The engine in your car typically runs at between 800 and 6,000 revolutions per minute depending on load. The reason the Wärtsilä runs so slowly is directly connected to what it is driving. The propeller of a large container ship is enormous, sometimes 10 meters in diameter, and it operates most efficiently at low rotational speeds. The engine is matched to the propeller, not the other way around. The result is an engine that turns slowly, but with a force that is almost incomprehensible in its scale. The physical dimensions of the RT Flex 96C match the numbers. The largest version of this engine, configured with 14 cylinders in line, stands 13.5 meters tall. That is taller than a 4-story building. It is 26 meters long, it weighs over 2,300 tons. Each individual cylinder has a bore, meaning the diameter of the cylinder, of 960 millimeters, nearly a meter across. Each piston, moving up and down inside that cylinder, displaces 1,820 liters of air and fuel mixture with every stroke. For comparison, the total engine displacement of a typical family car is around 1.5 to 2 liters. A single stroke of a single cylinder in this engine displaces nearly 1,000 times that volume. The fuel consumption of the RT Flex 96C is equally staggering, though in a different way than you might expect. The engine burns approximately 6 tons of fuel oil per hour at full load. That sounds enormous, and in absolute terms it is. But here is the critical context. The ship powered by this engine can carry over 18,000 20-foot shipping containers. The fuel efficiency per ton of cargo moved per kilometer is actually competitive with, and in many cases superior to, road freight. The scale of the machine creates an economy that smaller engines simply cannot match. The engineering challenge of building something at this scale goes far beyond simply making the components bigger. Every part of the engine has to be designed to handle forces and temperatures that push the boundaries of material science. The cylinder liners, the sleeves inside which the pistons move, have to withstand combustion temperatures exceeding 1,500 degrees Celsius, while simultaneously being cooled by seawater circulating through channels in the surrounding structure. The fuel injection system has to deliver precisely metered quantities of heavy fuel oil into cylinders, operating at extreme pressure at exactly the right moment in every combustion cycle, hundreds of times per minute across all 14 cylinders simultaneously. The crankshaft, the rotating shaft that converts the up and down motion of the pistons into rotation, is a single forged steel component over 12 meters long and weighing over 300 tons. The assembly of an engine at this scale cannot happen in a conventional factory. The components are too large to transport assembled. Instead, the engine is built in sections, with major components manufactured at specialist facilities around the world and shipped to the assembly site where the engine will be installed. In many cases, the engine is partially assembled in a dry dock before the ship is built around it, because the engine itself cannot fit through any door or hatch that would be practical to include in the vessel's structure. The reliability demands placed on a marine engine of this type are unlike those of almost any other machine in existence. A container ship crossing the Pacific Ocean is at sea for weeks at a time, thousands of miles from any port or repair facility. An engine failure mid-ocean is not just an inconvenience. It is a catastrophic operational event that can cost millions of dollars per day in delays, emergency towage, and cargo disruption. The RT Flex 96C is designed to run continuously at full load for intervals of up to 30,000 hours between major overhauls. That is over 3 years of continuous operation. Every component, every seal, every bearing, every fuel injector is engineered to that standard. The maintenance that does occur is carried out at sea by the ship's engineering crew, working in conditions that would be unrecognizable to most engine mechanics. Access platforms built into the structure of the engine allow engineers to work on individual cylinders, fuel systems, and bearings while the rest of the engine continues running. The modular design of the RT Flex 96C means that a malfunctioning cylinder can be isolated and taken offline without shutting the entire engine down, allowing the ship to continue its voyage at reduced power while repairs are made. There is also a question that almost nobody thinks to ask about an engine this powerful. How do you stop it? A car engine stops when you turn the key. A machine producing 107,000 horsepower directly connected to a 10-meter propeller through a shaft as thick as a tree trunk cannot simply be switched off. The stopping process involves a carefully managed reduction in fuel delivery, a controlled reduction in speed, and in some cases, the use of the engine itself running in reverse to slow the rotation of the propeller and the ship. The stopping distance of a fully loaded container ship traveling at cruising speed is measured not in meters but in kilometers. The engine is part of that braking system. What all of this adds up to is a machine that exists at a scale most people will never directly encounter. The Wärtsilä RT Flex 96C does not appear in car magazines or technology reviews. It does not have a consumer audience. It sits in the hull of a ship, invisible to the passengers and consumers whose goods it carries, running continuously for years at a time, converting fuel into motion on a scale that makes every other engine in everyday human experience look like a toy. Now here's something that deserves its own moment of attention. The fuel this engine burns is not the same diesel you would put in a truck or a bus. It runs on what is called heavy fuel oil, sometimes referred to in the industry as bunker fuel. This is the lowest grade of refined petroleum product, a thick, viscous substance that is almost solid at room temperature and has to be heated to around 130 degrees Celsius before it becomes fluid enough to pump through the engine's fuel system. It is essentially the residue left over after all the more valuable refined products, petrol, diesel, and aviation fuel, have been extracted from crude oil. It is cheap precisely because nobody else wants it. And the Wärtsilä RT Flex 96C burns it with a thermal efficiency of around 54%, meaning it converts just over half of the energy contained in the fuel into useful mechanical work. That is an extraordinary figure. The petrol engine in a family car achieves thermal efficiency of around 25 to 30%. The most powerful engine in the world is also, by a significant margin, one of the most thermally efficient internal combustion engines ever mass-produced. That efficiency matters for reasons that go far beyond the operating costs of a single ship. Container shipping carries approximately 90% of the world's traded goods by volume. The clothing, electronics, food products, raw materials, and manufactured components that move between continents do so almost entirely on container ships powered by engines like the RT Flex 96C. The fuel efficiency of those engines has a direct impact on the cost of almost everything that crosses an ocean. A less efficient engine would mean higher fuel costs, which would mean higher shipping costs, which would ultimately mean higher prices for consumers at the end of the supply chain. The engineering decisions made inside a machine that most people will never see directly shape the economics of global trade. There is another dimension to the story of this engine that rarely gets discussed, and it concerns what happens when an engine of this class approaches the end of its operational life. A marine diesel engine is not simply scrapped when it is no longer serviceable. The components are far too valuable for that. Cylinder liners, pistons, connecting rods, and crankshaft sections are assessed, and those that meet the required tolerances are reconditioned and returned to service as replacement parts in other engines of the same family. The metallurgical knowledge embedded in a forged crankshaft that has run for 30,000 hours is not thrown away. It is studied. The wear patterns tell engineers exactly how the stresses have distributed through the component over its service life, and that information feeds directly into the design of the next generation of components. The engine is not just a machine. It is a source of data that makes future engines better. The company behind the RT Flex 96C, Wärtsilä, is a Finnish engineering group with manufacturing and service operations in dozens of countries. The scale of the global support infrastructure that surrounds these engines is almost as impressive as the engines themselves. Spare parts are held in strategically located warehouses around the world, positioned to minimize the transit time to any port where a ship might need an emergency component. Field service engineers are on call around the clock. Remote diagnostic systems allow Wärtsilä's technical centers to monitor the performance of engines at sea in real time, identifying developing problems before they become failures. The ship's crew changes ports. The engine never stops being watched. And the next generation of this technology is already in development. Wärtsilä and its competitors are working on hybrid propulsion systems that pair large diesel engines with battery storage and energy recovery systems that capture heat from the exhaust gases and convert it into additional electrical power. Ammonia and hydrogen-fueled variants are being tested, with the goal of eliminating the carbon emissions associated with heavy fuel oil combustion entirely. The regulatory pressure from the International Maritime Organization, which has set binding targets for the reduction of shipping emissions, is accelerating that development considerably. The most powerful engine ever built is in the early stages of becoming something cleaner, something more complex, and if the engineering works out as intended, something even more efficient than what already exists. That is what I find genuinely extraordinary about this. The most powerful engine ever built for commercial use is also one of the least known. It moves the world's goods across its oceans with a quiet, relentless efficiency that the global economy depends on completely, and almost nobody knows it exists. Now here is something that connects directly to what we just covered. If the most powerful engine in the world runs at 100 revolutions per minute, what happens to all that energy when the ship needs to slow down, stop, or reverse in the confined space of a busy harbor? The answer involves a system of engineering ingenuity that is just as remarkable as the engine itself. That story is already waiting for you in another video.